So this is not only going to be an addition to your air freshener notes or smell notes, whatever you call them. It's also going to be your review for the quiz on Wednesday. This is what's on it, okay? So the first thing we have to do, or the main thing we have to do, is we have to talk about these models of different phases. So we have 3 different phases, okay? We have solid, and we have liquid, and we have gases, okay? I should just say gas. And I'm just going to draw a box that represents like a container with an object in these phases within it. Okay, so first of all, let's think about the arrangement of particles. Like, we should have learned, well, let me ask you, so let's make it a discussion so you guys contribute with me. Solids, liquids, and gases, what do you now know? What do we now know after doing that assignment yesterday? What are some differences between the particles in different phases? Like, what can you tell me about, hey, the particles in a solid are different from the particles in a gas, maybe, because why? Can you tell me anything from that? How would they be different? Okay, Josh just said particles move slower in a solid. Do you guys agree? I'm just going to jot down a note so I can remember when we draw this. Cool. So does that mean these other phases, the particles move faster then? Is that the same thing? Liquid slower than gas. You guys all agree with that? So the particles in a solid move slowest. Liquids move a little faster. Move faster. Move fastest. Okay. Most fast. What is that? How do you say that? All right. Anything else we can say about the particles? Okay. Odessa says they're closer together in solids. Does anybody disagree with that? Alyssa, you agree? Ashley, you agree? Jade, that sound good to you? I'll take that blank stare as a yes. Yeah, I would agree. Don't you think? Particles in a solid are closest together. All right. So what does that mean about the other phases in terms of how close together the particles are? Spread out more? Okay, are they spread out more in a liquid or in a gas? In a gas, they're spread out the most. Spread out most. Again, this is what you're quizzing on. Next week, you're going to do this. Exactly like this. Okay, so I'll just say spread out more here, maybe. Is there anything else we can say about the arrangement and or motion of the particles in the different phases? What's that? They're all connected? What do you mean? They're all connected in all phases? In solids, they're all connected. Okay? I'll jot that down. We might have to clarify that. Jerry, you were going to say something? Okay, it's so just to clarify something, it's not really it's something we talk about later, but usually when we talk about chemical bonds, those are within the substance, but there is something that are kind of holding them in place, right? They can't just move around freely, can they? Okay. Can I say stay in one place? Stay in one place for liquids? They move around a little bit. How would you describe that motion? Back and forth, kind of like just jiggle around, back and forth. Okay. So here's how I usually explain this analogy with my students. When you think of particles in a phase, you guys are all in desks. You have somebody maybe that sits behind you, and somebody that sits in front of you, and somebody that sits to the left of you, and somebody that sits to the right of you. You're all moving a little bit, whether you're breathing or maybe you're moving your hand to write something, or maybe you're looking at another student and making faces or something like that. But you're all moving, but you're all staying in the same spot. Or maybe you're looking at your cell phone in your lap as if the teacher doesn't know that you're looking at it. But like, for example, even though you're moving, the Josh particle is still going to be here in front of the Nathan particle. And he's going to be to the right of the Devante particle. Going to be to the left of the Megan particle. Okay? You're not changing positions. But what can happen is when we go to the liquid phase, it would kind of be like you guys then stand up and start walking around. And then you're changing places. So in the liquid phase, the particles are going to move a little faster. They're going to spread out more. And then they can change position. Okay. Now, if you get to the gas phase, using my analogy, what would that be like? Leave the classroom. What else? Huh? Go out in the hallway. Just keep going. Just keep spreading out wherever you can, right? Whatever room is available to you. And what about the speed? Would you just be walking? Yeah, you'd probably start running, wouldn't you? Okay. And if the door's not open, you probably wouldn't go into the hallway. What would you do? You would run and bounce off the door, wouldn't you? Okay, you guys would be bouncing off the walls. All right. And if you were at the level of particles, you would even be able to go up in the air and bounce off the ceiling and the floor, and then the walls, and then the door, and then all over the place, and each other. All right. So these are moving faster, spread out most. And the particles, I'll just say, go everywhere. Everywhere available. Okay, so I'm going to make these models, and again, using our modeling norms, paying attention to conservation of mass. Let's say I have a substance that's going through each of these phases. So that means I want to pay attention to the number of dots. I always want to make the number of dots the same. Why? Law of conservation of matter or mass. Yep. Okay. So I'm just going to make, I'll make this substance red. I should make a key. I'm just going to say particles because I don't really know what we're talking about. And I'm just going to make 4 dots because that's easy to, well, maybe I should make more. Let's make 6 dots. Okay? So in a solid, they're going to be close together. All right? So there's my solid, 6 dots. And then in a liquid, they spread out more and they can change position. And the other thing that happens is because they can change space, position, they are going to be affected by gravity. And that kind of pulls them down and makes them just kind of flow, right? So liquids can flow. So maybe I'm going to, instead of being like up in a block like this, maybe now they come down something like this. I want to make sure they're a little farther spread out. Okay. Maybe something like this. Still 6 particles. Okay. And then the last one, they can go everywhere. So, yeah, top, somewhere in the bottom, on the side, maybe over here, maybe over here, maybe up here. All right. So our newest thing for modeling norms is these arrows for movement. And we said the longer the arrow is, the faster the particle is moving. So correct me if I'm wrong, but aren't the particles moving fastest in a gas? Okay. So on these, and when you make the arrows, it's very important. Everybody looking at me? This is how you're going to do well on your first quiz for second marking period, right here. I'm going to draw arrows. Which direction should I make the arrows go? Any direction you want, just random. Okay? So when you make these arrows, just make them random directions, and you want to make them kind of long. Okay? So something like that, maybe. Maybe something like this. 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 Okay? So that shows me the particles are moving. And because we know the longer arrows mean faster, it means they're moving pretty fast. And in a liquid, they're going to move also, but they're going to move slower, right? So we're going to do some smaller arrows maybe. Still random directions though. Maybe something like that. Maybe something like this. Okay? And then solids are moving the slowest, and they're very close together. It's going to be hard for me to draw arrows in here. So this is what we're going to do for solids. And this should probably go with our modeling norms. We call them motion lines. All right? So we're just going to kind of show that they are moving. They're just jiggling back and forth. The arrows kind of represent that the particles are actually moving around, okay? And we know with the solids they're not. Their movement is more just kind of back and forth, bouncing off each other, okay? So what we do for that is we make these little like, they look like quote marks really around them. So like quote marks, I would do them around the individual particles if I had more room maybe. But as long as we add some of those quote marks, these are called motion lines. And what those show is that the particle, we can even put them like underneath or on top. Okay? But that's showing that the particles are just kind of jiggling back and forth. Okay? So for solids, you just use those quote marks. We call them motion lines. Okay? So on your quiz on Wednesday, that's exactly what you're going to be doing. All right? So we want to pay attention to what we know about how energy affects motion. What do we say about that? Energy affecting motion of the particles. Heat. Temperature. If I heat something up, would the particles move slower or would they move faster? They move faster if they're hotter? And does that make sense? Like if we had a solid and we added heat to that, that maybe it would become a liquid that's actually moving faster, maybe a little more spread out? Okay. So, and that is today's success criteria. I can describe the behavior of particles at different temperatures. So I'll stop the video here. We are going to watch one more of those short little videos, actually two short videos. Just jot down main ideas, and then we'll move on from there.